Saratech, and I will be your host today. We are fortunate to have David Corolla, Technical Director of Additive Manufacturing here at Saratech, with guest speakers Ashley Eckhoff, Marketing Manager from Siemens PLM, and Ken Burns, the Technical Sales Director from Forecast 3D. Here with us today to talk about design for additive manufacturing with Siemens NX and HP Jet Fusion 3D printers. Today's agenda will cover key considerations for design for additive, Siemens NX additive software capabilities, design for additive manufacturing tips using MJF technology, in-house versus outsource, followed by a Q&A. Please feel free to enter any questions or comments you may have into the chat box on your GoToWebinar control panel at any time throughout the webinar. We will address these questions in the Q&A portion of our webinar. And just to give you a little background on Saratech, Saratech is an engineering consulting company that provides software, engineering services, and manufacturing solutions to help customers optimize product development. We are Siemens and HP's #1 partner in the Americas. And if you're local to the Orange County area, we just opened our brand new Additive Manufacturing Technical Center in Laguna Hills. This Thursday, December 14th, we are having an open house, and you are more than welcome to join us. I would now like to introduce you to David Corolla, our Director of Additive Manufacturing at Saratech. He's a degreed mechanical engineer whose career focus has been in additive manufacturing. He started using the technology at Northrop Grumman and owned his service bureau for 7 years. He has had the privilege of working in new developments in the additive manufacturing industry, including patents on new actuation systems developed using additive. And I will now hand the reins over to David.
Thank you very much, Monique. And so one other thing I'd like to just add on to Monique's comment about the open house on Thursday. If you are interested in attending, we actually are having a few different sessions. So if you do have interest in that, please reach out via the chat box or email to inquire about that. And we'd love to send you over the invite for that open house. So getting right into our topics today, since we have a short time, primarily wanted to focus on design for additive in this webinar. And so I'm going to start by addressing some key fundamental considerations for design for additive. One of the first things I'd like to start with is kind of putting a common myth from additive to bed, that design complexity comes for free. And while that is still a very compelling reason to use additive, there are a lot of aspects that have to be considered when adding design complexity to a component being printed. So in the beginning of that, we want to really understand the fundamentals of additive, and per ASTM, they've defined 7 modalities that additive technologies fit into. We won't go over all of these, but you can see them on the screen in front of you. And this is one of the key things that you want to start with when you're considering designing for additive, is first understanding what technology is going to be used. So in this presentation today, we're primarily going to be focusing on powder bed fusion, which is what HP considers their technology. On top of this, you also want to consider the fundamental way that your cross-section is actually being created. So some of the 3 primary ways to consider the cross-section creation is what the industry kind of calls point. So if you want to consider this shaded area, the cross-section of whatever your geometry is, you would have actually a laser or a extrusion element in the case of FDM or fused filament fabrication, actually tracing out that entire geometry, right? Contours, infills, things like that. Then you go to what is considered swipe, and this is more along the lines of the HP technology, where you actually have an array of potentially print heads or an array of actual extrusion elements, whatever that may be, passing over the entire geometry. Then you have the third method, which is considered flash. And there are a few technologies out there right now, primarily using DLP technologies that would be considered flash technology, which actually expose the entire cross-section at one time. So when you combine this factor with those 7 modalities, that will then give you a much better feel for the actual process, and that will then allow you to then determine, whether or not you are going to have support structures, how those support structures might actually interact with your part, layer thicknesses, material properties, things like that, that will actually go into account when considering, how you're actually processing and creating your parts in additive. Another big consideration that people don't really think about too much when approaching design for additive manufacturing are, what are your software capabilities? Because design for additive can be a fairly iterative process, and primarily factoring in the 4 areas that I identify below here, it can become a very cumbersome process if you don't have the right software solutions that can be interlinked, and it can also be very confusing when you're going between multiple software solutions. So that's another big factor to consider when designing for additive. Why isn't this progressing? Sorry, I probably didn't. Sorry. There we go. So even though design complexity doesn't necessarily come completely free, it still is or can cost, quote unquote, cost less than other manufacturing solutions. So you definitely still want to consider a lot of factors such as benefits of part lightweighting, part consolidation, which is a big key aspect of additive, right? Taking an assembly that, let's say, for example, may have been injection molded and needing to be that way because of tooling part lines, things like that, and consolidating it into singular parts. And then also, performance gradients, as I've kind of called them here, where you can actually control the geometry internally to help with things like frequency tuning and mass distribution, things like that. So those are definitely things that you can benefit from additive in your design process considerations. I won't go over all these because it's fairly wordy, but we will have this presentation available for distribution. But here I'm just outlining some key considerations and questions you want to ask when selecting and choosing your ideal parts for design for additive. That is probably one of the biggest areas that I see companies even wasting a lot of time, is choosing parts that, great, you may be able to improve through additive, but aren't really truly utilizing additive to its full potential. And so these are just some key questions that you'll want to ask, or you'll want to have your engineers ask themselves as they look through files, to determine whether or not it's an ideal candidate for designing for additive manufacturing. And then just going into kind of applications and areas that you might want to consider additive for and designing for additive. Really it depends on how advanced you are as a user. Ideally, and I think where Ken will go into more detail, and also Ashley, I should say, if you can start from the initial concept with the idea of additive manufacturing in mind, that's the most ideal. That's where you'll be able to get a considerable amount of your benefits for designing for additive manufacturing. But this chart really kind of shows, and especially for aerospace, I think I would argue that this chart is good for quite a few different industries. But ultimately, you can see some of the areas that additive has the most potential for impact for companies. Additive is traditionally been used for the design phase, as you can see here, but from the cost benefit and the biggest ROI right now, especially, that comes into manufacturing, tooling aids, things like that, where you can actually have a bigger effect on your organization than just creating better designs or quicker designs up front. So that's a consideration as well for selecting your parts for designing for additive manufacturing. Going into a little bit more detail on the solutions that Saratech specifically offers. We are a software reseller, and the software focus is part of our DNA. And so we do team up with a lot of software companies to provide solutions for engineering workflows. A big focus of ours, and especially in our teaming with Siemens, is the workflow for additive, seeing how it is a very new technology to consider from a full portfolio perspective. And so I'll let Ashley go into a lot more detail on that. Saratech also, which is very not very well known to our customer base, I should say, is our engineering services. So we do a substantial amount of engineering services for companies, contract services, one of which can be considered also design for additive manufacturing. So if you want to consider design for additive manufacturing but aren't quite sure how to approach it, how to start with your engineering organizations, that's something that you can absolutely come to us and contract for, and we can help walk you through that. Another aspect is training or professional development. So, what good is, softwares and hardware without, training solutions? And so we have an entire team that can do training courses. We have training courses that are pre-developed, as well as we can do training courses custom developed for your organization. So that's a consideration for how we can help you out in the design for additive manufacturing realm. Manufacturing solutions. So not only will we help you on the front end, help you determine the right additive solution, for your parts, but we also can take that additive solution through the complete manufacturing process for your organization. We have done this quite substantially for a few aerospace customers, and would love to help you out if you have that need. And want to even consider, purchasing equipment or doing larger production efforts through companies such as Forecast. And then obviously we focus on additive manufacturing as well. We are a approved reseller of multiple different types of technologies, including plastics and metals. And something that we really pride ourselves on is the integration with our engineering solutions team. And so making sure that we identify the proper technology from the get-go. Even if you do come to us with a prime technology in mind, we will evaluate that with you and see if that's the right solution for your needs. So that wraps it up for my slides. We're going to have Ashley from Siemens up next, and then Ken Burns from Forecast 3D as well. So I'd like to turn it over to Ashley.
Thank you, David. Appreciate it. Let's see, am I presenter? Perfect. Okay, so my name is Ashley Eckhoff from Siemens. I will warn everybody that I came down with a cold this weekend, so I'll do my best to work through this without coughing in everybody's ear. One of the things at Siemens that I think people maybe don't know so well, a lot of people know that we make things, right? So we make trains and controllers and medical equipment and things like that. But Siemens also does software, and a big portion of that is CAD software that can drive additive manufacturing machines. So I've been with Siemens for about 20 years. In fact, almost exactly 20 years. At the end of this month, I will have my 20-year anniversary with Siemens. And during that time, I've seen a lot of different things change over the years. But Siemens, as far as additive goes, has been in this game for quite a while. The Siemens as an entire company started research in additive way back in 1989. And that was not but a couple of years after the initial stereolithography machine sort of came out and that patent hit the market. Since then, we've done all kinds of various different research and development using various different additive technologies, sort of in fits and starts as the technology itself has matured. And especially in the last maybe 5 years, we've really made a large investment in this area, especially on the software side, trying to come together with tools for our customers so that they can effectively create parts using additive manufacturing methods. So like I said, Siemens is a company that actually makes things, right? So we have several different divisions of Siemens that not only, do we make software, but we're also actually making parts with additive manufacturing. So the guys in the energy division are manufacturing various different parts like turbine blades, burner heads that they repair using additive, things like that. And then we've got the mobility division, which is making custom parts for their various different trains in various different cities across the world. Where they move people, mass transit from one place to another, and each one of those applications might call for slightly different tweaks on the formula, and so some of those custom parts are made using additive manufacturing as well. What's really interesting about those parts in particular is that the restrictions or the certifications for materials used in a train are actually many times more strenuous than those used for aircraft, which you wouldn't expect. But several years back, there was a couple of accidents on trains where they caught fire and caused a bunch of deaths. And so the restrictions for the materials you can use and fireproofing and things like that are actually very strenuous. So we've had to go through a large amount of internal research and development to certify materials that we use with additive manufacturing for use in those applications. And it's a lengthy process, but again, it's sort of giving you an idea that Siemens doesn't just write software about this stuff. We're actually making these things out in the field, and all the information we gain from that, we bring back and try to use to make our software better for our customers as well. So internally and externally, I guess, when we talk about the opportunity that additive brings to a company, we talk with our customers, we see that a lot of people are still in this what we call the status quo, where they're either not using additive or they're maybe using it to do prototypes, right, which is the standard reason people pick up additive manufacturing. But we think there's a lot of opportunity being missed if you just locate yourself in that one little box down on the left there. One of the opportunities is the opportunity to reimagine products. So, being able to take a product and totally redesign it from the beginning for an additive manufacturing method at the end gives you a lot of freedom. You can reduce weight and material. You can do things like topology optimization. You can totally rethink about the way that part was designed, knowing that you're going to additively manufacture it. It also allows you to do a lot quicker turnaround if you are doing, prototyping of those parts, getting those parts and that iteration done much faster. There's also an opportunity on the manufacturing side. You can either eliminate castings and moldings by, printing things directly, final parts, or you can also think about printing your molds, things like that we're seeing come online a lot, and a lot of people thinking about ways of doing that, reducing the cost of those molds, especially for things like first 100 prototype molds, where you can, print out a plastic mold, generate about 100 injection molded parts with that, and then, the mold is no good after that, but you can iterate onto the next version and do that very quickly and very inexpensively compared to having a full mold machine. The lead time is severely reduced, and so is the cost. It also allows you to do things like affordable low volume production, so if you have things you want to, you just need like 50 of them rather than 50,000, additive again is something you can think about for those types of parts. If you've gone through those different transformations, you've looked at reimagining your products, you've looked at reinventing your manufacturing, then you can really start to think about how does this affect your entire business. You can start to think about making custom parts for people if they order them. You can start thinking about zero inventory, right? Getting rid of your big warehouse full of parts that just sit there and you pay for the warehousing of, and instead building parts on demand as people need them. You can also think about distributing printers across the planet or using service bureaus in various different areas to print parts for you closer to the area of demand so that the logistics and the shipping and the lead time come down. Things like that are things you can think about once you've kind of gone through the process of reimagining your products and rethinking how you do your manufacturing. You can get to the business aspect of things as well. So we kind of talk about all these various different aspects of additive with our customers. We talk about the opportunity here for people to change the way things work. Now, one of the problems we see in the industry right now is a lot of people have what we consider to be a disjointed process. They have various different pieces of software. Some of those are pieces they bought. Some of them might have come with the printer. Some of them maybe even be, freeware, depending on how, what machines you're driving and what processes you use. But the problem with this is that all those different pieces of software require translations, dumping data out of your normal systems back, bringing that data back in. Half the time you probably have to rework that data. All of this is number one, it's a time drain, but number two, it also encourages errors in the process, and you lose data fidelity. Things like PMI don't carry across often in those translations, and it requires a lot of rework. So we see a lot of problems with this disconnected process chain, and one of the things we are driving towards is a vision where we have all the major pieces necessary for an end-to-end additive solution built into a single process with a single uninterrupted data chain from beginning to end. So this includes normal product design. It also includes generative design, topology optimization, lightweighting, being able to take the things that result from those processes and use them natively with more design, so editing those things after they come back, being able to validate those things, set them up inside of a build tray, generate the code needed to send to the printer, print that part out, validate that part at the end, and then finally have a final part to deliver. Our goal here is that all of this can be done inside of a single end-to-end system, because we feel like if additive is ever going to move from just a simple prototyping tool into an actual industrial manufacturing tool, that you need this uninterrupted data thread from beginning to end for lots of different reasons, for traceability, for error purposes, for quality. So our goal is to build our system so that it includes all of these things that we think our customers need, and of course connecting all that together with data management, shop floor connectivity, and some MOM and MES systems as well. So towards that end, we've made a lot of partnerships in various different places. So we've got the partnerships we've made with various different hardware vendors. So these are the companies that actually make printers, right? So DMG Mori, EOS, HP, Trump, Stratasys, Sayaki, and there's more in there as well. We're always adding new partners to our stable because we're trying to cover as many of the possible technologies our customers will need and make sure that those things work well with our software. Then we have some software technology partners, various different things they do that we're maybe not so good at, or we think that they're maybe the best in the market at. We work with them to take their pieces of software and to integrate those into our process. So again, you can have all the advantages of using those various different technologies, but have it in that unbroken data chain from beginning to end. We've also made partnerships with consulting services, material partners, again, just trying to make sure we have all of our bases covered here so that our customers can have that unbroken digital chain from beginning to end. So we support a lot of different technologies for this. David talked about the different modalities. So there's powder bed fusion. We support several of those different machines from different manufacturers. There's directed energy deposition, which we partnered very early on with DMG Mori. In fact, I think our software is the only software that can drive those machines, and I believe you get a seat of our software with those machines when you buy them. Very high end, very impressive. If you were at Formnext a couple of weeks ago, you were able to see those machines. Really cool stuff. There's fused deposition modeling. We've worked on some pretty interesting stuff with Stratasys over the years on that. We've got a demonstrator that does some multi-axis fused deposition modeling that's pretty interesting. You can look that up on the web. There's videos of it. But for today, I pulled out HP multi-jet fusion. It can be considered basically a powder bed technology, but I'll call it out today since that's what we're talking about. We have a nice partnership with HP. That partnership started over a year ago. We actually started talking to HP before we ever announced the partnership to the world, but that was over a year ago now, and we've since strengthened that partnership with some other activities as well. But what it's allowed us to do is it's allowed us to work sort of hand in hand with HP to make sure that the software we're writing can properly drive the printers they're building. So we're now certified for use with multi-jet fusion printers in the 3200 series and the 4200 series, including the 4210 that they just announced Formnext a couple weeks ago. This gives us a direct integration. So basically you can design your parts, you can do all the analysis, the topology optimization, the lattice structures, all that stuff you want to do to a part, validate it, and put it in a build tray, print it out directly to an HP printer without ever having to, like I said, export that data or break that chain of digital thread from beginning to end. We've also done some interesting stuff with them here on the research side, and I'll talk about that here in a minute as well. So what do we have that's interesting for people who want to print using HP printers from a software perspective? So Siemens, we have a product called NX. It's our high-end CAD suite. And one of the technologies that's built into NX is a technology called, oops, I don't know why that went on its own, called convergent modeling technology. Now, convergent modeling allows you to use facet bodies, B-rep bodies, and surfaces all together at the same time without regard to where the geometry came from. So the progression you're seeing here in these pictures, the first image is a STL facet body that came from HP. That body was, it's facets, so it's not exact CAD geometry. What I've done is I've taken an actual B-rep cylinder, so I just designed a cylinder inside of our CAD system and subtracted that from that facet body using convergent modeling, right? So I'm interacting between B-rep geometry and facet geometry. I created a new area there in green that has some fins on it, a little cone, and I united that back into the original solid. That solid can then be taken and sent right back down to the printer at the end for a final print. So it allows you to take things like topology optimization or lattice structures who normally come out as facet bodies and use those directly with normal modeling techniques in your downstream operations, absolving you from a lot of redesign. We also, of course, have the standard simulation tools inside of NX. So this is a flow simulation I did on that same duct. So we have flow simulation, we have thermal simulation, we have structural simulation, all the things you'd want in a normal CAD tool. The things that are coming along here very soon are the thermal simulations for actual laydown of material. Excuse me. So the thermal simulation will give you a layer by layer simulation of how the material is being laid down, how the material is performing, where you might have warpage, where you might have heat buildup, things like that. And that'll be coming online here in the next couple of months or a month or two, I think. So a final piece of software to focus on here with regards to HP is nesting. So we partner with Materialize to build their nesting solution into our software. Basically, it allows you to optimize the build volume for an HP printer by packing as many parts in as possible. And you can set things like how the part is oriented, whether it's free orientation like I did in this case, or whether it's fixed in various different degrees. And the other thing that's important here is that I've got this in the mode where it optimizes the height. So what it will do is once it gets all those parts in the build volume, it will start to crunch them down and crunch them down and crunch them down, trying to push them down as much as possible. And this is good for the HP printer because printing in the Z direction takes longer than printing in the X and Y direction. Here, I'll run that again just so we can watch it play. And so what that does is it saves you some time and it saves you a little bit of it gives you more efficiency in your build process if you can crunch those parts down at the end and get them as close to the original build tray as possible, saving you basically the time it takes to build other layers, which takes longer than going in the X and Y planes. So again, partnering with people in the industry that we feel have really good technologies and bringing those into NX. What you see here is Materialized technology under the hood being used with NX user interfaces, NX parts, and NX data. So again, the data never has to leave. It's never translated. It's still, native NX data here being used with the code we've partnered with Materialized for. So one of the other things we've done with HP in the past year, and one of the things our partnership has given us is the ability to work with them on some interesting prototypes for future applications of additive manufacturing. HP doesn't print metal at the moment, but they have been doing research in that area. And so one of the things we showed back at our analyst conference in September was a prototype we did with them where they actually printed out this gear rack for us. And the theory behind this is the gear rack has some embedded traces inside, and as the gear rolls back and forth on that rack, it wears away the material and it also wears away those traces. And as the traces wear away, the resistance on them changes. So What that means is that we can sense when the part is worn out as opposed to having to replace the part on some sort of schedule. So if you kind of take this idea and you build it out over time, you can imagine, every hinge, every bearing, every gear rack like this, any type of moving piece inside of a piece of equipment that can get worn out can now theoretically have an embedded circuit inside of it that tells a central processing unit when that piece is worn out. So you no longer have to take machines offline on some sort of set schedule, which may not be ideal. And instead, you're only taking them offline when the parts have actually worn out, and you can replace the parts then and hopefully save the downtime that you would have working the way we do today with some sort of set schedule. So these are the types of things that we're working with HP on, our modeling, driving their machines, doing things that are really interesting and really driving the future forward here as far as additive manufacturing goes. So just to reiterate, we have, trying to get this entire workflow into our system from the original design all the way down to the final part, including things like topology optimization, lightweight structures, being able to take those bodies from wherever they're from, be they facet bodies or exact bodies, CAD geometry, work with those things together without having to do all the redesign, validate them, put them in a print bed, slice, hatch, print them, post-process them, run them through inspection, and then finally get the final part out. Again, we think that in order for additive manufacturing to become a true industrial solution, this is the sort of workflow that has to be from end to end without breaking that data chain, because you need that sort of traceability, especially in areas like aerospace and medical, where they, if there's a failure out in the field, they need to understand the entire process so they can understand where that failure came from and address it properly. Those are the sorts of industries that are going to require this unbroken data chain that we're working to implement here. And the good news is that all these pieces of software you see here today are available in NX right now. So just to reiterate about our partnership with HP, we are certified for use with HP Multijet Fusion 3200 and 4200 series printers. Again, that does include the new 4210 as well. We have integrated design, simulation, manufacturing, validation, all the stuff you need to take apart from the beginning all the way down to that direct integration with the HP printer, so that you never have to translate data, you never have to lose fidelity, you never have to worry about introducing errors into that process. And we've reinforced our partnership with HP as the years have gone on here, making sure that we align with them and work with them on some really interesting things for the future as their technology evolves and our ability to drive that technology, making sure that it evolves in lockstep as well. So that's pretty much it for me. We do have some information on the web, so if you would like to get more information about what we're doing with additive manufacturing, not just the HP stuff, but everything involved, we have this nice landing page, siemens.com/plm/additive manufacturing, all one word. That will get you to a web page where we are basically putting everything that's publicly available about what we're doing with additive, and we keep that up to date with what's going on inside of our software development as we release new versions and as we think about things for the future. You can look there. We also have an NX manufacturing forum where people get together and discuss manufacturing, additive manufacturing and other manufacturing types. And we also have an app available in the Google App Store or Apple Store, allowing you to basically, it coalesces a lot of the various different pieces of data we have publicly available and brings it together in a nice form that you can read at your fingertips. So that's it for me. I'm going to pass things over to Ken, so I can figure out how to do that. It's all you, Ken.
Great, thank you very much, Ashley. I'm pulling up the presentation here. Hopefully everyone can see my screen. So I'm Ken Burns, I'm with Forecast 3D. I'm the technical sales director here. I got about 8+ years in the additive manufacturing world with 2 different service bureaus, Forecast being the second. I was also formerly with Stratasys on the materials team there. Got hands-on experience with lots of different technologies here, so pretty much all the major ones out there in the market space. So just a quick brief overview of Forecast and who we are. So we have been in business for about 23 years, founded in 1994 by Donovan and Corey Weber. And we got our first 3D printer in 1996. That was an SLA printer. We now have 32 industrial printers comprised of 5 different technologies. We can print anything plastics, composites, all the way to, we have metal printers as well. And we've recently added 12 of the HP multi-jet fusion printers in our newly opened 3D manufacturing center, which just sits next to our Carlsbad headquarters. We also have some traditional services, CNC, RTV casting, resting in our about 50,000 square feet of space between the two facilities. We're about 100 employees. Predominantly, we serve customers in North America, but we frequently will support customers throughout the world. So I'm going to just speak briefly today on design for additive manufacturing, specifically focusing on multi-jet fusion. Again, I say specifically multi-jet fusion because the DFAM rules apply differently to different technologies. And so we want to look at these ones. There are some general overlying rules, but as you're probably aware, when you go into different technologies, there are different rules you need to abide by. So taking a look at this graph here, this is just kind of giving an overall view of when 3D is introduced into the development cycle. And we're specifically focusing on new products here, not existing products in the market space. So this is something that's new in your organization. So there's 4 different levels here where I'm going to kind of discuss of when is ideal and how it kind of affects the ability to influence additive manufacturing in there. So first is that the manufacturing analysis here. So additive is picked for an economic advantage. Moving up the ladder here, if we're looking at part design phase, designs are typically optimized for additive manufacturing at this point. We go further up, we're looking at not just the part design, but the whole product architecture. So you can take combination of assemblies and create them into single parts. And then finally, at the top of the ladder there, we have product definition, which there's unique value only possible through additive manufacturing. So again, kind of focusing at the top point there, as you can see in the graph, the opportunities are greatest, as you would expect, that you can really identify solutions for additive manufacturing that are not only economically more viable than maybe traditional options, but they could be logistically or strategically beneficial as well. So I want to discuss just a few high-level rules for designing for additive manufacturing with HP systems. And these ones are focused specifically on the systems themselves. So there's a few rules if you have one of the systems themselves that you need to abide by when identifying parts there. These will also apply to designers or companies out there who maybe not have the system in-house but are sending parts out, just to understand why certain parts or geometries may not be efficient for the process. So identifying the build direction is important. And this is kind of a common thing with most additive technologies, but the accuracy in the XY is better than the Z. So understanding tolerances on your part and how they need to be oriented. And then having curved surfaces facing downward. This is important for some of the aesthetics of the parts there as well, and how some of the thermal energy builds up there. So a second point there is avoiding sudden changes in printed surface area. One of the big reasons for this is because it can decrease the thermal buildup. Too much thermal buildup in certain areas of your printing can cause surface defects or even part failures on it. And then draft into build sections to split up surfaces. So again, maybe putting parts at angles there or a draft on them so that you don't have too much thermal buildup in one area on the part. And then thinking about pack density. So this may seem obvious, but more parts equals less cost. That's less cost per part. So if you can pack more parts in there, you're going to save on your cost because of the efficiencies of the printing process. And then part diversity matters. And what I mean by this is that sometimes printing the same parts over and over and over stacked on top of each other is not as efficient as adding multiple different diverse parts in there, because they can complement each other well and improve some of the other efficiencies of the computer, like decreasing the thermal buildup. Simple example on the side over here, as we will move into the next few slides and some of the other considerations for the designing for MJF, is a simple injection molded design part here versus an additive manufactured design part. So you can remove a lot of the unnecessary material that's in the part. Remember, these are rules that are guided by injection molding, not by additive. And so taking out certain angles or additional just material in those parts in the sections labeled 1, 2, 3, you can see where they've been removed, and a much more cost efficient model for additive, where if you printed that in injection molded design, you're not going to really recapture all your savings in the part. So moving into a few, or I guess 6 different kind of points here for considerations. We'll get some specific examples. So first is angles. And so what I mean here is just the angles of the parts. Hard edges, corners can make it difficult to remove powder from the part. And this is important because the powder removal process, if you can't automate it, adds labor to it. And in manufacturing processes, obviously we want to decrease the amount of labor in there to keep the cost down. If we start getting difficult parts that are difficult to remove the support material from, which is the powder, then it could be difficult to successfully print them or clean them. Second, we look at cavities or holes. And so what I mean by this is, again, I mentioned the last one there, that the powder itself is the support material in this process. And so any sort of deep cavities or holes can require manual cleaning of the powder material, which means you're going to drive up the cost and the manufacturing side of it. So it may be efficient for 1 or 2 off prototypes, but in the production side, probably not a realistic path to go down. Third, packing density. So again, we mentioned this, if your part is 3 inches tall in the Z height, then your entire path there is going to cover 3 inches. So if you print 1 part or 20 parts, it's going to take the same amount of time. So packing density is really important on these. And also important because you're able to maximize your material usage in there as well. You don't want to use a lot of dead material in there when you're having to repack with virgin powder in there. Next is draft or stackability. So I did mention before that part diversity is good, but some parts will play really nicely in the system, and you can, if you can design in some draft like you would in injection molding, the ability to stack these parts, you can become really efficient in how many parts you can put in the build. Next is abstraction or a foldable design. So if you consider maybe the standard design on this part, it was completely rigid on it, and there was no ability to bend the part, but in the ability to change the manufacturing method and just have this bend in there and it snaps into place, you can now stack these parts inside of the build there and print a lot of them rather than maybe just a few of them at a time. So adding some foldability design into parts. And then communication. So this one is not necessarily a specific rule for how you design the part, but really important to consider all the steps in the process. So if your product consists of 1 single part, it may be a little bit easier, but a lot of products out there in the world consist of multiple components that mate with other parts, and different departments might own some of the design or manufacturing methods on them. So the communication between the different departments of how these parts are going to be made is really important, because you can gain efficiencies and ensure that everyone understands how these parts made up, right? Tolerances might be a little bit different in additive processes, so how these parts made up with other parts is something really important to consider. So looking at your full product development life cycle there, just ensuring that the communication starts in the beginning and it's all the way through supply chain. So I'm going to give a couple of examples specifically on the nesting side of designing for additive manufacturing and just where the benefits really come into it. So this first product here is just a typically or a standard design part, a little cap here with tabs on it. If we took this part as designed and put it into the multi-jet fusion printer, this is on a 4200 printer, by the way, we could fit 42 of them on one build platform. By simply adding some cutouts in this cap, we're able to now stack these parts, and there are no design restrictions that wouldn't allow it to have these cutouts. It just wasn't manufactured or wasn't designed that way from the beginning. So the increased quantity goes from 42 to 210 in one build here. So quite a change here on how many you're able to print in the build. And the standard thing with these printers is you're going to max on your print time. So the print time is about the same. It's about between 12 and 15 hours for these parts, whether there's 42 of them or 210. So the pricing on this, as you can imagine, if you only print a few of them, the price is going to be much higher because you're not maximizing your full build capacity there. But as we scale up there and we go to, we just ran the numbers up to 1,000 here. The ability to not be able to nest these parts very well, the price is a little over $31. And then the small design change drives that price down to just over $8 a part. Again, these are our costs to going outward. So internally, you might figure your price a little bit differently. It depends on how you do your cost model. Another example of the nesting process here is taking this simple cup and throwing that into the build platform as designed. We can get about 75 of them in there. Again, by adding some simple draft to the parts here, and there were no limitations to this product specifically from the customer. So this is something I was fully able to do there. You can now change it and get about 360 parts inside of the build. So again, increasing your throughput on the system there. The cost difference here, you cut about in half, went from about $26 a part all the way down to just over $13 per part by just slightly changing that design there. And we didn't remove any of the material necessarily, just literally the draft on the part. So hopefully those were a few good tips on there. I know it wasn't super detailed in there. I just want to give a few quick ideas of how you can gain efficiencies in the MJF process there. I'll briefly just cover the benefits of in-house versus outsource when you're looking at having parts made. There's a few considerations here. We are a company that does the same exact thing. Maybe your company does, but we consider if we're going to buy a printer, if we're going to outsource the work, depending on a few different variables. So resources, this is an important one. Do you have the resources internally to support running the system? While it looks like a nice little desktop 2D printer there, those things are much bigger than a 2D printer and require a lot more care and maintenance in them. And so do you have the expertise or sources, operators to run those systems? If not, considering how you might want to outsource that versus bringing it in-house. Materials is important. So are you looking to run one material in-house all the time, or do your products require different materials, flexible, rigid, composites, whatever it might be on there, and kind of understanding that balance. If you're making 80% of your parts in ABS, then it might make sense to have a printer in-house and outsource the remaining 20% for whatever materials those are. Those ratios are flipped. It might not make as much sense to bring something in-house. Volume, specifically as your product cycle, are you prototyping only 2 months out of the year, and the rest of the 10 months your machine's going to sit there, you're going to be looking for work on it, or you have a high volume where you're constantly making new products and year-round you're requiring service on them. And again, what's your utilization rate on that system to understand your ROI? This one I bring up specifically more looking at the HP systems. Are you looking for prototyping or production? Their systems are designed, while you can do prototyping on any of them, the 4200, 4210 are focused on the production side. So are you looking to do production in-house or prototyping in-house? And there's definitely considerations there as far as what you might need as secondary processes for post-finishing to meet specs for production side or assembly or whatever that side might look like on there versus prototyping. So a good consideration to have also production. You might not want to interrupt your printer if you're doing production stuff on it for prototype work. So understanding how you're going to utilize that system internally to make sure you calculate a good ROI. And then finally, just the other consideration, there's facilities. May seem obvious, may not, but definitely important to consider is, do you have facilities to support this, from electrical to air to heating and ventilation, all these different aspects. And processing, there are additional equipment that goes with most printers out there. It's not just a printer. You have processing stations or support removal stations, finishing stations, whatever it might be. So do you have the facilities to support those different pieces of equipment? So hopefully that was helpful. I appreciate your time. I'm going to pass this back over to Monique to kind of run through any sort of Q&A. Thank you very much.
All right, thank you so much, Ken. And just to do a quick little summary recap of what was covered today, we went over the key considerations for design for additive manufacturing, Siemens NX additive software capabilities, design for additive manufacturing tips using MJF technology, and in-house versus outsource. So we are now at our Q&A portion, and we actually received a couple questions in. So Ken, Jeremy Rowland asked, when nesting multiple and different parts, is there a concern of surface quality being different on the same parts as they are stacked in different positions?
No, once we typically with customers will identify the orientation that is ideal for whatever surface finish they need. The upward facing surfaces are different than the downward facing surfaces right now. So once we identify an orientation, we are typically locked into that and we don't change. So no matter where it's located in a build, it won't impact it. The only thing I could say there potential could be an impact on it is parts that the part diversity we talked about. So if there's the wrong part nested up against it where it could cause additional thermal buildup on it, it could cause some defects to the part surface on it.
Okay, awesome. And then one more question from Deep Test. She says, is secondary machining operation required to separate the parts printed in the matrix?
No secondary machining. The parts are just supported in the powder that it's actually being built by. So you simply just pull them out of the powder, depowder them, and then they're ready to go. Now you might want to do some additional finishing, media blasting. Different media can have different effects on the surface finish there, but no machining required on them.
Okay, awesome. And if anyone has any other questions, please feel free to type them in. Oh, got one more in. Let's see. All right, so, and we actually got a couple more questions. So Greg Smith asked, to get a painted part, is there any special prep required?
Sorry, can you say that one more time, Andy?
It says, to get a painted part, is there any special preparation required?
No, we printed parts or painted parts straight on the surface finish there. Depending on what color you're going for, primer, probably a good thing. Surface finish, it just really depends on what you need. If you just want a different colored part, you can paint them. We also like dyeing the parts. Nylon materials dye really well. The HP material naturally is gray, so dyeing them a bright like yellow or blue or something is difficult because you're dealing with a base color that's already dark, so you get typically deeper colors. But we've experienced with a lot of different colors with high success. Currently, we do black as our main one because that's easy to dye on gray.
Okay. Kevin asked, what about a Nitronic 60 part? Is that something you're familiar with?
I'm not familiar with that question. If it's directed for me, this is Ken.
Okay. Deep Tesh also asked, tested parts performance in high vibrating systems.
I'm assuming the question is. Go ahead, David.
Go ahead. I was just going to say, so for example, high vibration applications, like military or things like that. Have you had any experience with that?
I can't speak and say that we've absolutely had any experience with our customers doing that. I wouldn't doubt it. I will add, nylon 12 or the nylon 11 or nylon 12 glass build that are coming out in the MJF systems, they have the same properties as basically injection molded materials. You're not sacrificing that. So if you take a spec sheet and put it side by side with that, you're going to get basically similar performance in X, Y, and Z axes on there. So it's much different than other technologies where you don't get the homogeneous properties in them. So if your part works in a vibratory application injection molded part, we would expect no different performance from a MJF part. Hopefully that answers.
So we actually got some clarity on some of those questions. So the high vibration was referring to metal printed parts. So if you have any input on the materials that you guys are using in the metals technologies, and then also the Nitronic 60 is high temperature stainless steels. So along the lines of those metal materials as well, which I believe you guys are doing a stainless, right?
Correct. Yeah, we currently run a couple of different stainless steel metals and then aluminum in-house. Our systems can run any metals material. We just kind of our applications with our customers have driven us towards those materials primarily in the last 6 to 8 months on there. So again, I would say I wouldn't expect if you're having these parts made in traditional ways. Typically, the rule with metals printing is better than cast, not quite as good as raw. So hopefully that's clear enough. If there's further clarification, then maybe we can take that one offline, or that can be directed, definitely another question added on there.
And then another question from Sharon Moore on when will Forecast offer the glass bead nylon material?
As soon as HP ships it to us. So hopefully they've announced the material. Yep, go ahead, David.
Go ahead. No, go ahead.
We are just waiting to get the material received. It was announced, and we're just ready for it whenever it's available in the U.S. here. So we are currently offering the nylon 12 and nylon 11, just not the glass bead yet.
So we have a couple other questions. I think we do need to wrap it up, but just to address, we will follow up with the individuals that ask these questions, such as, are you doing carbon printing? The answer is yes. So we'll address some of the more specific questions in a one-on-one. We'll reach out to you, and we appreciate your time. Monique, if you want to address any last-minute items.
Great. Thank you, David. Thank you to our presenters, Ashley and Ken. Excellent presentations today. And to all our audience members, we will be posting this video to YouTube later today. If you need to refer back to anything, feel free to pass along to your friends and colleagues, and be sure to subscribe to our channel, follow us on Twitter and LinkedIn for upcoming webinar dates and topics. And if you could please just stick around for about 10 seconds afterwards to fill out our survey, let us know how we did and what you liked. We really appreciate everyone for attending today, and have a great rest of your day.